Hello and welcome to another video. In this video we're going to be working on find the number of coins to place in tree nodes, and that's going to be the last problem of the Biweekly Contest 120. And I think it's about the same level as the one before, honestly. So in this one, you're given an undirected tree with n nodes labeled 0 to n minus 1, with a tree root at 0, and a 2D integer array edges, where edges I, a to b equals, there's an edge from nodes ai to bi in the tree. And if you know for a tree, if a tree has n nodes, it has n minus 1 edges. So that's always going to be the case. So like in this case, it'll have 6 nodes and 5 edges and so on. And you're also given a 0 indexed array cost of length n, where cost I is the cost assigned to the node. You will need to place some coins on every node of the tree. The number of coins can be calculated as, if the size of the subtree is less than 3 nodes, place 1 coin. Otherwise, place an amount of coin equal to the maximum product of the cost assigned to 3 distinct nodes in the subtree of I. If the product is negative, place 0. Return an array coin of size n such that coin I is the number of coins placed at node I. So in this first example, basically at node 0, because you can have any coins you want, here all the costs, so you would just take the biggest 3. So here you would get 120, and then at every other one, the subtree is only 1 node, so you would place 1 coin. In the second example, at this 0, you have any coin you want, so you would place 5 times 7 times 4 times 8, which is 280. At this 1, you would place the maximum 3 of 3451, which is 140, I think. Yeah. And then at 2 is the maximum of 2678. So 2 is 2, and then 678 is this, so it's going to be like 2, 2, and 8, which is 32, and then at every single other one you place 1 coin. And in the last example, you would place, let's see here, you'd place 1 coin here, 1 coin here, and then all the costs are these. So you'd actually want to place 0 here because the maximum cost would be negative, because the 3 coins that you could place here would be 1, negative 2, and 2, which would give you negative 4, which is less than 0. So you'd place negative 1. And here are the constraints and a bunch of other stuff. So first, what you want to learn is, I did draw a tree here, but before we even get to this tree here, let's actually draw out an array of numbers. Like let's say we have some things to choose from, right? We have some node, we have a bunch of values to choose from, and let's make the values sorted just to make it easier. Let's say we have values like negative 9, negative 8. That's the other thing, is you can have negative costs. 5, actually not 5, let's do negative 7. And then let's do maybe like 1, 2, 3, 4, 5, 6, 7. This will demonstrate it pretty well. So if you're asked to get the product of 3 nodes here, you might think like, well, I should just pick the 3 biggest nodes. But in reality, actually, there are 2 scenarios that you want to look for. One is going to be 3 biggest nodes. And there's another case where, since the product of 2 negative numbers is positive, you can take 2 negative numbers and multiply them by a positive number. So which 2 big negative numbers would you pick? You want to pick the 2 most negative numbers, because that would give you the biggest product, times the biggest positive number. So that's the other case, which is 2 smallest nodes times biggest nodes. And so that's what you're gonna like. The best one is always gonna be one of these 2, or they'll both be negative. Like let's say every one of these was negative, then you would just get a negative number, and then you would just write 0. So for every node, what you really want is you don't need this whole thing, right? You don't need to store this whole thing. Like let's say for a node, if we had values, all we really need is the 2 smallest numbers and the 3 biggest numbers. And like this stuff doesn't really matter because we're never going to use it. And so that's kind of the idea behind this problem, is as we build our tree, and like for this node, let's say we can use all of these. We don't really need all of them. We just need the ones we care about. And so the easiest way to do this is going to be, we're going to be building our trees. This is still like the hard part of this problem. Now that you know, like, okay, I only need the 2 smallest and the 3 biggest, and that's all I need to keep track of. It depends how you build it. Like for example, here, if you have the 2 smallest and the 3 biggest, that's not going to work, right? So let's say here the 2 smallest is going to be like negative 9, it looks like, and negative 5, I think. And the 3 biggest will be 1, or not 1, 8, 7, 6. So if we store it like this, if we store it like this, the problem is if we divide this into further like chunks, it's kind of hard to know what goes where, right? And the problem is if you keep subdividing, like you might have actually had some numbers in here that you needed. Like if you had all these numbers, you actually needed to divide. Like if you start at the top and you divide down and you make these arrays smaller and smaller and smaller, it's kind of difficult. So instead, we're not going to build our tree that way. We are going to start at leaf nodes and build up. And it's going to be a little counterintuitive how to do this. We're basically going to need to do, so let's kind of like figure out what this would look like first. So essentially what I wrote here is the like index of the node, right? And also notice they don't really tell you that the tree, they don't really tell you anywhere in the problem that the tree has to be in this order. It's not always going to be like 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 is on the top, but it can easily be like 0 and then node 5 and then node 7 and so on and so on and so on. So you're not guaranteed to have this like BFS order. So instead what we're going to do is we're going to have a DFS. We're going to start at the top. We know it's node 0. We're going to connect. We're going to make a graph that's going to connect every node to every other node that it's connected, or not every other node, just to the nodes that are given in edges, right? So we'll build this graph. Then we'll start at node 0. Then we'll have a visited set. And the way it's going to work is because this is an n-ary tree, it's not a binary tree. Like any node can have multiple children, right? Any node can have more than 2. I just wrote it like this. So some node can have like 5 children and so on. These aren't balanced or anything. So what we're going to do is we're going to actually do a DFS from the top. And we're going to say, okay, let's check every child. And if the child isn't in visited, and we're also going to store, actually, do we need to store? No, we don't need to store. So if the child isn't in visited, if we haven't visited it yet, let's recurse down to it and let's get the array of this like 2 smallest and 3 biggest, right? So like let's get that array of 5 elements, or it could be less, right? You might not always have it. And then let's return it up, and then let's combine these arrays. So let's kind of show how this is going to work. So essentially we're going to start at 0, and so remember this is node 0 and the value is -5. So the cost will be -5 and the actual index is 0. So we're going to start here, and then we're going to say, okay, for this left node, have we visited it yet? No. And as we go into it, we'll mark it as visited. So I'll just like color it to make it visited. So we're going to go into this node, we're going to mark it visited. Then we will say, okay, is this child visited? No. And the reason you want to visit it is because you don't want to traverse back and forth, right? Like you don't want to go from 5 to, you don't want to go from node 0 to node 1 back to node 0 and so on. So by marking it visited, you're guaranteed traversing down. So we'll go here and we'll say, is this visited? Okay, it is now. Now we're going to check the left child again. We're just going to go through all the list of children, so there might be a bunch. We're going to say, is it visited? No, it isn't. Okay, is this visited? No, it isn't. And now there are no more children. So this array that this is going to return, well, we can actually get rid of this now as well. We can get rid of like all of this. And here we have, how many nodes do we have? We have 14 nodes. So let's draw that out as well. So let's make an array of 14 nodes. So let's just say this is this. And let's have a couple more of these. So we need 6 more. Or 5 more. So we should be able to just throw that there. And add these indices over here like this. So 10, 11, 12, 13, 14. Did I screw that up? Maybe I did. No. Okay, so I guess I had an extra one. Okay, so there we go. So we're going to figure out like what these arrays are. So for this one right here, this only has one node. So for all of these, this is all going to be marked as, I believe we want to mark them as 1s or something. Let's double check. Yeah, if the tree is less, we place 1 coin. So for this 7 through 14, we'll just place 1 coin. We can do that now because they're all going to be 1. But yeah. Okay, now here we want to return, remember, the 3 biggest and the 2 smallest, but there's only 1 value here, right? So because there's only 1 value here, we will just return that value in an array. So we will return -2. Now here, there's only 1 value as well. We're going to go right, and we're going to say visit it, then return -2. So instead of actually showing this for every single node, I'll just write the thing up here. So the 2 values we're going to get are -2 and 2. And we are going to sort them, right? And we're not going to have enough values here either. So for all of these, for this 3, 4, 5, 6, this is all going to be 1 as well, because there's not going to be enough. So these are all going to be 1s. Okay, so this is the 2 values that will return up here. And so we can do that for all of these like nodes, because that's going to be I could show the flow of it first. So essentially we'll return up here, we'll go up to this node, then we'll visit this node, we'll go to this node, we'll go to this node, then we will come back up here, then we'll do the right side. So we'll go over here, go over here, go over here, go over here, come back up, right side. So all of these, we'll just show what we're returning in here. So so here we will return -5 and 7. And then for this node number 5, we will return there's not too much space here. We'll just write it over here. So it'll be -9 and 8. And for this 3, remember, we're just taking the nodes for the children, sorting them, and then only keeping 5, the top 3 and the bottom 2. But because here we don't have enough, we're going to store it like this. Okay. So now coming up here, now we'll finally have enough nodes. So we're going to take the 2 children, and we're going to combine them, right? We're just going to take all of the children and combine all of those arrays, sort them, and then only keep 5 nodes. So let's put these in. So once we sort it, it'll be -5, -2, 2, 7. Now, basically, like I said, we either have the 3 biggest or the 2 smallest times the biggest. So in this case, it's going to be the 2 smallest times the biggest is going to be our better answer, right? So it's going to be these 2 times this. So our answer for this one is going to be 70. So there's 70 that goes here. And we will return this array, right? Because this is 4 elements. We're returning only 5 though. Now when we build up, like let's say our array was a ton of elements, we wouldn't need to return them all. We would only, if we had a big array of like, let's say we had like -9, -8, -7, so on to like 7 or 8, 9 or something, we would only return this part and this part, because once we're building up, we're never using this middle part and the thing we're building up. Like those values are redundant. So we will only return an array of length 5, which is what's going to make this pass. Is you're not returning like in a whole array of numbers. You're keeping a very small array and you're returning only an array of length 5 maximum or less, right? Because these are less. Okay, so now let's look at this side. So we're going to sort these 2. So we're going to have -9, -2, 3, and 8. So I think I also did miss a few values. Actually, now that I'm looking at it, yeah, I definitely did. Yeah, so let's fix these up a little bit, because what happened here is I did return these 2 values, but you also want to include the node itself, right? So let's just double. So these should actually have values. So let's fix these. So let's fix this. Yeah. Okay. Yeah. So let's fix these and these, and I'm just gonna write them on the side because that is something I did forget. So for the node, we want to include the children plus the node itself. So let's just get rid of this, and we're just gonna write it on the side over here. So for node number 3, for node number 3, the array is actually going to be this -2 and 2 and -3, right? It's the children plus the node itself. So we are going to have enough values here. So it'll be -3, -2, 2. Now, like I said, it's either going to be the 3 biggest or the biggest and the 2 smallest. In this case, it's the same value, but in this case, it's going to end up being 6 times 2, so 12. So here we do have 12. And let's get rid of this value here. Okay. Now let's go through 4. So 4 will have 7, -5, and 6. So sorted, that'll be -5, 6, and 7. And now here, this is going to be negative. So you're just going to want to place, I think when it's negative, they said like place like -1 or something. Let's take a look. Yeah, if it's negative, place 0 coins. Okay, so we're going to place 0 coins at 4. And then we're going to go to 5 and 6. So for 5, it's going to be these 3 here. So -9, 1, 8. And so this is also going to be negative. So we're just going to place 0 coins there. And at 6, it's going to be -2, 3, also negative, so we'll place 0 coins there. Okay. Now we can build up these like future ones and then this last one. So for 1, it's going to be 3 and 4 and this coin itself, right? So it's going to be, so let's take a look what that'll be sorted. So that'll be -5, -4, -3, -2, and then it'll be 2, 6, 7. Okay. So this is going to be what it is for 5. Now remember, we don't need to store this whole thing because we will either take the 2 smallest times the biggest or the 3 biggest. So what's going to be the answer here? First, let's get rid of unnecessary information. So we can just keep -5, -4, and 2, 6, 7. So get rid of everything else. -5, -4, 2, 6, 7. Yeah. Okay. And so what's going to be the best result here? So this is going to be 42 times 2, so 84. Or it's going to be these 2 times 7, which is 20 times 7, so that's 140, so that's better. So for 5, or this is not going to be, sorry, it's not going to be for node 5, this is going to be for node 1, right? Yeah, it's going to be for node 1. Okay, so yeah, the better answer is going to be 20 times 7, which is 140, so we'll write that in. And we will return this up to node 0. Now let's go and do node 2. So node 2 is going to be all of these values plus the node of 2. So sorted is going to be -9, -2, 1, 2, 3, 3, 8, I believe. And so the better answer there is, what's this going to be? This is going to be 9 times 8, which is 72, or it's going to be this thing. So 18 times 8 is obviously going to be better. So 18 times 8 is 144, I think. Yeah. So we're going to store that. So 144. Now, when we build up this last one, we basically need both of these. So let's move this over here. Let's copy it, and the value for 0 is -5. So essentially, we have both of these two arrays, and we have a -5. So sorted, that's going to be, and we can also get rid of some of these values because, like I said, we don't need all of them. So we only need the biggest 3 and the smallest 2. So there we go. We only need these values, and then we need maybe the -5. So once this is sorted, this is going to be -9, -5, -5, -4, -2, and then the positive values are 2, 3, 3, 6, 7, 8. We can get rid of all the unnecessary stuff, so that's going to be all of this. So we basically have -9, -5, 6, 7, 8. And so 6, 7, 8 is going to be, that's going to be kind of annoying actually, 56, 330, I think, or 336. Yeah, 336. Alternatively, we could do this, which is 45 times 8, which is 320. Yeah, so this one's bigger for sure. Yeah. So this is 320, 360. So that's going to be the better number. And so that's kind of how you do it. So essentially, we just keep track of only 5 numbers maximum, and we just DFS down. And anytime we go somewhere in the DFS, we will just visit the digit to make sure that we're not like looping, back and forth and back and forth and back and forth through the tree. And then we will just like have an output array, and we will write everything into. So let's look at the code. And so here it is. So first we build an adjacency list just from like the edges, and we make a visited set, and we make a result. And then now we do a DFS. So we're going to call it on node 0. And essentially what we do is we add it to visited to make sure we don't go there again. And then the array of values that it's going to have is going to have its own value. And then for every child, if the child hasn't been visited, go down and get its array and add all those arrays together, sort the array. If the length of the array is greater than 5, take the 2 smallest and the 3 biggest. Otherwise, if the length of the array is less than 3, then just put in 1. And if the array is like 4 elements or less, we don't need to do any kind of like getting rid of stuff. We can just keep it as is. Now you can optimize it a little, because let's say your array is like something like this. Like in my code, I'm just storing this, but in reality, you're never going to need these numbers. So you can optimize it and like keep the 2 negative numbers and the 3 positive numbers, but it just works to keep the 2 smallest and 3 biggest as well. And then basically these are your 3 cases, right? So either take the 3 biggest, multiply them by each other, or the two smallest times the biggest, or if these are both negative, then just take 0. And that's pretty much it. So if we run it, it should be pretty good. And there we go. And essentially the time here is basically going to be n log n, because so where n is the number of edges. Now edges and nodes, like I said, edges and nodes for a tree is going to be basically the same thing, right? Edges is just nodes minus 1. So essentially when you build these up, you're going to be taking nodes from other, you're going to be building arrays from other arrays. And so the maximum like children you'll have total or something is something like n. So you're essentially it's going to be like 5n that you're going to be taking for children. Also, when you do like let's say you have an array of length n, if you subdivide that array into a bunch of chunks, like if you subdivide that array into like a bunch of chunks that are, let's say, like n over 2, you know, or like n over 3, and so on and so on and so on. If you subdivide it into a bunch of chunks that all add up to n, and you sort all of those chunks, each of those chunks is going to be n log n, where n is the length of the chunk, but all the chunks are going to add up to n. So in reality, this is going to be like, you know, if your array is like length 10 and you subdivide it into like, let's say 5, 3, 2 or something, then it would be like 5 log 5 plus 3 log 3 and so on. And so these are never going to be worse than just 10 log 10, right? So worst case scenario, it's going to be n log n of the entire array, but the more chunks you subdivide it into, like these sorts are going to be faster and faster. So anytime you have an array that you subdivide into chunks and you sort the chunks, that's going to be upper bound complexity of n log n, where n is the entire array. Okay, and then space. So let's see what we created here. So obviously you need to have the actual like graph. So that's O of n, visited set, O of n, result doesn't count. And then recursive call stack is going to be O of n as well, right? Like let's say your tree is just entirely right shifted, where it's like node 0 has a right child of node 1, node 1 has a right child of node 2, and so on. Then you would have all those would just be O of n. Yeah, so kind of a lot of an explanation there, but yeah, I think this is a kind of cool problem. And like I said, even if you know how to do it, it's still kind of tricky to like, how do I take these arrays of numbers and actually build them up? And like I said, you can just do it with a DFS like this. You can try to build them up from the bottom with like a BFS or something, but it gets kind of confusing because you don't really know what level you're at in your tree, because you don't have to be like, your tree can be completely unbalanced, and then it's like, what do you do? Like, what if your tree is like this? Let's say, you know, where like it could be something like this, and then it's kind of like, where are my leaf nodes? How do I build this up or something? So DFS works a lot better. Yeah, it's gonna be all for this one. So hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I'll make the videos for the contest at the end of the day and in a while as well. So thanks for watching.